Hello everyone and welcome to my CompTIA A+ 1101 video series. In this video we will review Objective 2.3, which covers the 802.11 standards, their frequencies, speeds, and various versions from the past. We will also take a quick look at long-range fixed wireless, near-field communication or NFC, and radio frequency identification or RFID. There's a lot to cover here, so pause the video and take notes when needed. Other than that, let's go ahead and get started. Wireless networks are, for the most part, available in our homes and businesses. Most of us expect that when we walk into a restaurant, an office space, or even the park, that wireless internet access will be available. The standards for these wireless networks come from the IEEE Standards Committee. This is the IEEE 802 Committee, and the wireless networking part of that committee is 802.11 standard. These standards have evolved over the years and usually include better data rates, increased range, stable connections, and improved security. For the A+ exam, you will need to know about many different wireless standards. Instead of being referred to as 802.11 wireless networks, you often see that it's simply abbreviated as Wi-Fi network. This is a trademark from the Wi-Fi Alliance, a global nonprofit organization of companies that work to improve the user experience of wireless networking technology. If you want to learn more about the Wi-Fi Alliance, I'll leave a link in the description. The first standard we'll look at is 802.11a and is one of the very first wireless standards that was released all the way back in 1999. It's a standard that operates in the 5 GHz frequency range and maxes out at 54 megabits per second. Although this isn't fast now, back in 1999 when this was first released, that was a lot of speed for a wireless connection. Because it functions at the 5 GHz frequencies, we don't have the same connection distance as lower frequencies such as 2.4 GHz range that's used in 802.11b, which allows us to get up to a little bit more distance from the 2.4 GHz base network. 802.11a networks aren't used all that much today, and you probably won't see them around in any building or any other wireless network. They are considered a legacy standard. The 802.11b standard was finalized at about the same time 802.11a was being released. However, this is not an upgrade to the 802.11a standard as it functions with different frequencies and has different speeds. 802.11b works in the 2.4 GHz range and has a maximum speed of 11 megabits per second, which is a lot slower than the 54 megabits per second that we just discussed with 802.11a. At this point, why would anyone choose the slower 11 megabit per second wireless standard over a 54 megabit standard that was already available? This is because 2.4 GHz frequencies bounce off of devices instead of being absorbed. Because of that, we have a longer distance in 2.4 GHz networks. This, of course, will depend on the type of environment that the network is set up in. For example, if you have a lot of open space and not a lot of walls or obstacles, then you may want to choose 802.11a. But if you're in an office environment where there are a lot of walls, then you may want to choose 802.11b because that frequency works a lot better in that environment. The major downside to 2.4 GHz networks is that other devices use that range. Microwave ovens, wireless mics, speakers, and even some Bluetooth devices use 2.4 GHz frequencies. That means that you could have a lot of frequency conflicts and signal interruptions. Like 802.11a, it is considered a legacy standard. One of the first upgrades available to these 802.11b networks was the 802.11g standard. This was released in 2003, and just like 802.11b, 802.11g also operated on the 2.4 GHz range. This was great for anyone using 802.11b because it increased the speed on the G standard to 54 megabits per second, matching that of the 802.11a standard. This standard is backwards compatible with the B standard, which means that we could upgrade our access point to the 802.11g and still continue to use our B devices on the same network. Although 802.11g operates at higher speeds, it still uses the same frequency as 802.11b and therefore has the same type of conflicts with other devices that share or use 2.4 GHz in that area. However, 802.11g offers slightly better indoor and outdoor range than that of 802.11b. In 2009, a new standard was released that effectively upgraded 802.11a, b, and g to a new version, 802.11n. At this point, standards naming changed to using a Wi-Fi version, so 802.11n can also be considered or called Wi-Fi 4. Because 802.11n or Wi-Fi 4 is designed to be an upgrade for 802.11a, b, and g, this standard is able to function at both 5 GHz and 2.4 GHz at the same time if your access point supports it. We also have more bandwidth available for each individual channel, which increased to 40 MHz channel widths. This means that we're able to transfer much more data at the same time over this network. If you do have a wireless access point that's able to use those 40 megahertz channel widths and it has 4 antennas on it, you can get a maximum theoretical throughput of 600 megabits per second, a huge improvement over 802.11a, b, or g. This 802.11n standard also introduced a new form of communication for wireless networks called MIMO, or multiple input, multiple output. This means the network devices can transfer much more information simultaneously between the client and the access point. In 2014, 802.11ac or Wi-Fi 5 was released after being developed from 2011 to 2013. This was another improvement over the previous standard of 802.11n. Wi-Fi 5 functions solely in the 5 GHz frequency, so unlike 802.11n, there is no 2.4 GHz available. You may also hear it being referred to as Wi-Fi 5 VHT. This is because it produces a very high throughput over a 5 GHz frequency. This standard also changes how information is transferred. Known as signaling modulation, this also increased the amount of data that was able to be transferred at any particular time. 802.11ac not only uses multiple input, multiple output, or MIMO, but increases the capabilities by adding multi-user to that. So you have multi-user, multi-input, multi-output. So for example, multiple users could be communicating over multiple inputs and multiple outputs at the same time. This standard supports up to 8 multi-user MIMO streams, which translates into a maximum throughput of 6.9 gigabits per second. As I mentioned earlier, 802.11ac functions only on the 5 GHz frequency. But if you look at some of the access points that are available, you'll see that some of them say that they function at both 2.4 and 5 GHz frequencies. In those situations, 802.11n is using the 2.4 GHz frequency, and anything at 5 GHz is using the 802.11ac standard. The upgrade to 802.11ac arrived in 2021 with the 802.11ax standard, also known as Wi-Fi 6. This is a standard that operates at either 5 GHz frequencies or 2.4 GHz frequencies, and some access points can use both at the same time. 802.11ax was designed to solve some of the problems we have when we're using wireless networks in areas where there are a lot of people. So for example, if you're in a stadium or concert, you may find it difficult to send or receive texts or even make phone calls. With 802.11ax, a new form of communication was introduced called orthogonal frequency division multiple access, or OFDMA. This type of communication has been used for a while on cellular networks, and this brings this tech to the 802.11 standards. This allows us to put 802.11ax networks in places with a lot of people and be able to communicate without the struggle of messages not being delivered and phone calls being failed or not able to make any type of phone calls. Let's take a look at all of the different standards. 802.11a operated on 5 GHz frequencies and did not have MIMO support. Its maximum theoretical throughput per stream was 54 megabits per second. 802.11b operated in the 2.4 GHz range and had a maximum throughput of 11 megabits per second. So here, the range increased, but the speed decreased. 802.11g combined the best of 802.11a and b, as it operated at the 2.4 GHz for longer range and had a maximum throughput of 54 megabits per second. 802.11n networks can operate in either 5 or 2.4 GHz frequency ranges and can use up to 4 separate data streams of multiple input and multiple output. This gives us a total throughput per stream of 150 megabits per second, or a maximum throughput of 600 megabits per second overall. 802.11ac uses 5 GHz technology only. It supports 8 downloadable streams of multi-user, multi-input, and multi-output at 867 megabits per second for each stream, making a maximum total theoretical throughput of 6.9 gigabits per second. And 802.11ax operates at both 5 GHz and 2.4 GHz. It also supports 8 streams, but the multi-user MIMO in 802.11ax supports download and upload streams that can function at the same time. That provides a maximum theoretical throughput per stream of 1.2 gigabits per second and a maximum theoretical throughput of all streams at 9.6 gigabits per second. When the distance is too far for Wi-Fi but high-speed wireless network connectivity is needed, point-to-point technology can be used. This technology involves using directional antennas to transmit and receive network signals between locations, such as buildings in a city or a campus. The antennas must be positioned facing each other to establish a connection, and obstacles like trees and buildings should be avoided. The antenna resembles a small satellite dish, approximately 1 meter wide, is capable of transmitting and receiving signals at distances of 10 to 20 kilometers. It can support different technologies, such as Wi-Fi 5, 6, and cellular networking. Wi-Fi operates on unlicensed frequencies such as 2.4 GHz and 5 GHz, while other frequencies like 900 MHz and 1.8 GHz are used by devices like walkie-talkies and cordless phones. Unlicensed frequencies are free to use, but this also means that they are popular and more susceptible to interference and eavesdropping. Intercepting signals on these frequencies requires being within the range of the field, which is challenging but not impossible. However, licensed frequencies like those used for AM and FM radio require permission granted by a governmental body such as the FCC in the United States. Companies seeking to use licensed frequencies for purposes like long-range fixed wireless must also request and receive permission to do so. Power can be transmitted over long distances using fixed wireless technology known as wireless power transfer or WPT, which is regulated by the FCC in the United States. This method is similar to Power over Ethernet or PoE but operates wirelessly. WPT involves two stations, the transmitting station which generates the power and sends it via microwaves or laser lights to the receiving station. Then you have the receiving station which converts the signal back into electricity. An example of this technology on a much smaller scale is wireless charging pads for mobile phones. However, energy loss is a concern, with WPT having an efficiency rating of around 70% compared to traditional copper-based cable electricity. Radio frequency identification, or RFID, is a communication standard that uses radio waves for communication, and its entire purpose is to identify items within a short range. There are three types of RFID based on the frequency used: low frequency, which covers about 10 centimeters, high frequency, which reaches up to 30 centimeters, and ultra high frequency, which extends up to 100 meters. Examples of how RFIDs are used include managing inventory in a bookstore, identifying people through IDs, and tracking or identifying animals in farming applications. An RFID system consists of three main components: the tag, the reader, and the antenna. The tag is attached to any item that needs to be tracked and can either be temporary, like a badge, or permanent. It contains information such as employee ID or product numbers, and can be passive or active. Passive tags do not have a power source and draw power from radio waves provided by the RFID reader within a range of 25 meters. Active tags have their own power source, usually a small battery, and can have their own antenna. This allows them to be detected within a range of up to 100 meters. The reader, as you might have guessed, reads information from the tags. It has its own power source and antenna, and can detect the presence of tags once they come within range. Readers can be mobile, used as inventory trackers or scanners, and they can also be static, such as those found in security gates at retail stores. The antenna boosts the distance the RFID signal can travel, and some readers may have multiple antennas depending on the model. Last but definitely not least when it comes to wireless networking standards is NFC, or Near Field Communication. This is a subset of RFID, and it is a two-way wireless communication that is specifically created for sharing information easily. Its primary emphasis is on contactless payments. Operating through radio frequency signals, NFC functions in three distinct modes: card emulation mode, which enables the device to function as a smart card. Then you have reader-writer mode, which allows for reading information from an NFC tag on a label or a poster. Then you have peer-to-peer mode, which facilitates ad hoc data transfer between two NFC-enabled devices. An example of how NFC is used on a daily basis includes the following. First, the user moves their device within range, which is about 10 centimeters or 4 inches. Then, using an app, whether it is proprietary or downloaded, the device completes the transaction, such as making a payment, reading information, or transferring data from one device to another. And since NFC is heavily used in payment options today, it will likely be around for years to come.